Recording in progress. Great. For people watching this video later, we've been graphing things in 3 dimensions. We plotted some points and we drew some planes, and we're drawing another plane right now. So let me make sure I share my screen appropriately. Okay, good. I have. All right, cool. So to graph this plane, again, we're going to start with the. Now, you might notice every time I'm drawing this XYZ 3-dimensional coordinate system, I'm only drawing the positive parts. And that's because I've been picking examples where kind of the important things have been positive. But if one of my intercepts was negative, I would definitely be drawing the negative half of the axis as well. Here, my x-intercept is going to be, well, if I set y equal to 0, I'm going to get 2x plus 4, sorry, 2x equal to 4, which is going to give me x equal to 2. Now, technically, really, I'm actually setting both y and z equal to 0. Since z is in this equation, I don't really have to worry about it. Similarly, if I set x and z equal to 0, we're going to get y equal to 4. So here's part of what I'm graphing. And this line that's going through my x-intercept of 2, my y-intercept of 4. But just like the previous things we didn't have a couple variables, here we're also missing the variable z in this case. So that means that z is allowed to be anything so that we can extend this line upwards and downwards. It's kind of like, think about, oh, perfect. It's kind of like if you had a line and then you just decided to like decided to extend it downwards to make it into a plane. Kind of that's and upwards as well. I don't like things that are. I see. So we're just going to say, hey, this thing we can also make it go upwards. Like that. And also you can go downwards, but it's not going to make my picture look very nice. I'm just going to stop right there. So here's my plane, 2x plus y equal to 4. And you don't need to draw these little arrows that indicate that it goes on. Everyone who's going to be looking at any work you do knows that you can't draw the whole infinite plane. You don't have to point out that it continues on and on forever and ever and ever. You can just draw part of it. All right, a couple more. So here's another one that's actually even easier. Let's say we have, sure, 2x plus 3z plus y equal to 6. And I've annoyingly written it out of order. It doesn't really matter that much, but I should do better. You should write your variables in lexicographic order, also known as alphabetical order, if you can. It's not super important, but it feels wrong to write them out of order. So to graph this also a plane, we're just going to find the x, y, and z intercepts and then draw the thing that we have. So if I set x and y equal to 0, I'm going to get 3 times z equal to 6. I'm going to get z equal to 2. So my z-intercept is 0, 0, 2. If I set x and z equal to 0, I'm going to get y equal to 6. And if I set y and z equal to 0, you're going to get 2x equal to 6. You're going to get x equal to 3. So if I start plotting my intercepts, I'm going to have y equal to 6. So 1, 2, 3, 4, 5, 6. Z equal to 2. 1, 2. And then x equal to 3. And something to point out is your x kind of, if you're making these little marks to like indicate lengths of a unit, your x mark shouldn't be as far apart, right? Because if you have something that's this long and then you've turned it so it's supposed to point towards you, it shouldn't look as long anymore, even though it's supposed to be as long as the other things. So your x marks should be spaced a little closer to each other than your y and your z marks. So let's see, I'm going to have z equal to 2, cool, y equal to 6, right? And x equal to 3. And then we're really just going to draw the connecting segments between those. So there's that. And let's make sure I get it right here. Whoops. Okay, close enough. And that. And I might label my intercepts. That's 0, 0, 2. That's 0, 6, 0. That's 3, 0, 0. You don't need to label your axes, but it's maybe good the first few times you do these things. Now, that's only part of your plane, right? It continues on in the directions that it goes in. So technically it's, continuing that way, and 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 that way. But really, once you have a triangle's worth of stuff, the triangle kind of defines a plane. So drawing just the triangular portion here is sufficient to be like, yeah, there's my plane. We're good. Something I would point out in 2 dimensions, when you have an equation where x and y are both raised to the first power, that's going to give you a line. For example, so just to mention, like whether it's like y equals 5 or x equals 3 or 2x plus 5y equals 14 or y equals 3x plus 7. Whoops, let's make it less blurry maybe. The thing that all these equations have in common is that x and y are either not there or raised to the first power. And all of these are equations of lines. In a similar way, in 3 dimensions, as long as all your variables are raised to the first power or aren't present, you're going to get a plane. Something kind of 3-dimensionally linear as opposed to 2-dimensionally linear. So in 3D, something like x equal to 5 or y equal to 2 or z equal to 1 or x plus 2y equal to 7 or 3x plus 2y minus 5z equal to 20. All of these are equations of planes. Once you start getting higher powers of your things, or like I should also mention, because it can be tricky, if you have x times z, not a plane anymore, even though they're both raised to the first power. So you can't have like things multiplied together that have kind of a higher degree. And I'm saying more about this than is really necessary because it's not that necessary. But let's talk about graphs of other shapes. And there's not a lot of other important shapes really, but there's one or two I want to mention. So what if I wanted to graph, say, the equation x squared plus y squared equal to 16? Well, in 2 dimensions, what kind of shape would that be? That not quite. If it was y to the first with an x squared, like something like y equal to 16 minus x squared, this would be a parabola. Parabola, yeah. But this equation where you have x squared plus y squared equal to some number that's often a square number, that's the graph of a circle. This is a circle in 2 dimensions. So in 2D, a circle. And it would look like, your usual circle of radius 4. In 3 dimensions, we're going to take that circle that's living in the xy plane and we're going to extend it in the z direction and get a cylinder. So we're going to so this is where I am going to draw like the full XYZ coordinate system. And where are you, green pen? Sure. So we're going to draw our circle of radius 4. Now, drawing the circle of radius 4 in the XY plane on the floor can be a little challenging, right? It shouldn't look like a straight on circle. It should look like a circle that's been kind of tilted down to sit on the ground. So it's going to look kind of like that. And then we're going to extend it upwards and downwards, but mostly just upwards because it's easier to draw that way. There's my cylinder of radius 4. X squared plus y squared still equals 16, right? No matter what point you pick, whether it's this point here, or this point here on the surface, or this point here on the surface, or some point like right here, all those points are still on a circle of radius 4. They just happen to have maybe a different z value than the one down here. So just like we saw already, when you're missing a variable, that means you get to kind of extend that graph in the missing variable's direction. So you take your two-dimensional thing and you just kind of like stretch it out in the z direction if z is missing, or in the y direction if y is missing, or in the z or in the x direction, which is always kind of challenging if x is missing. Let's look at kind of one more example of that. Yeah, we'll do that one. So let's say I want to graph sure. Z equal to y squared plus 1, which is a parabola. The convenience here, the nice thing I like about graphs that are missing the variable x is drawing in the YZ plane is just like drawing on your usual 2D plane. So we're first just going to draw the graph kind of as typical. So here's my y, here's my z, I guess here's my x. So we're going to graph z equal to y squared plus 1. So it's your usual parabola shifted up 1. So I got the point 0, 1, and I guess I can do one more here, sure. Try to make it look kind of nice. It's going to look like this. Usual parabola shape. But then x is allowed to be any value. So we're going to extend this in the x direction. So we're going to like essentially pull out this curvy shape extended, kind of like it's kind of like if you had like an accordion, right? Like those parabola shape, and then you just kind of pulled it out, it would be a long parabola shape. So it's going to look like here, this is always the hard part, it's drawing it. So I'm trying to extend like each part parallel to the x-axis, which is what makes this one challenging. A ruler would be really great. I should start bringing a ruler with me. So we're going that way, and then we're going to come down like this, and then hopefully it looks decent-ish, and then maybe up a little more. Yeah, like that kind of. So there's your parabola extended towards you. You can kind of think of it as looking like this, a piece of paper folded into a parabolic shape. And now here's maybe some slight bad news. You know what we call this? A parabolic cylinder. Anything with a few exceptions, but any kind of two-dimensional shape that you just extend in a third direction is called a that-shaped cylinder. I know, kind of weird. So like if you had a ellipse and you in two dimensions and you extend it in the third direction, it'd be an elliptical cylinder. Not something you have to worry too much about, but just wanted to make sure you're aware of the vocabulary. Okay, so the last the last three-dimensional shape I'm mostly concerned about graphing is the following. Yeah, we should use a new piece of paper, even though I don't really want to, but fine. Okay, so let's graph the following equation. We're going to graph the equation x squared plus y squared plus z squared equal to 25. And this kind of might make you think a little bit of the equation of a circle, but not exactly, right? Because you have a third dimension here. This is actually the equation of a sphere. So this is the equation I can spell words, the equation of a sphere whose center is 0, 0, 0, and radius is the square root of 25, which is 5. There's more to say here in a second, but first we'll just draw it. Drawing a sphere So drawing it is kind of a pain in that I would probably just kind of draw it first and then try to center my origin in the middle of it. So you could try drawing it like this and then saying, cool, here's my sphere. And then after you've done that, we say, okay, great. Now my center needs to go here. My z-axis goes this way. My y-axis goes this way. My x-axis goes this way. So right there's my point 5, 0, 0. There's my point 0, 5, 0. There's my point 0, 0, 5. Feels kind of like cheating, but it's all right. I guess we should also have the right here's my y-axis going that way. Here's my x-axis going that way. Z-axis going that way. So yeah, kind of funky, but okay, what if we have sure. So here's a new question, kind of related. We want to find the center and radius of the sphere given by the equation x squared plus y squared plus z squared plus 8x minus 6y plus 2z equals -17. And you might notice this sphere is not written in what we would call the standard way of writing the equation of a sphere. Just like there's a standard way of writing the equation of a circle, where it's like x minus the x coordinate of the center squared plus y minus the y coordinate of the center squared equal to the radius squared. The same thing is true for a sphere. We really want to write this as like x minus something squared plus y minus something squared plus z minus something squared equal to our radius squared. And what that requires is for each of these x squared plus 8x and y squared minus 6y and z squared plus 2z, completing the square for each of those three different variables. So here's what we're going to do. We're going to rewrite this as x squared plus 8x plus leave yourself a space for what we're going to fill in. And then y squared minus 6y, leave yourself a space. And z squared plus 2z, and leave yourself a space. And it's equal to -17 plus whatever's in those three spaces, which I wish I had more room for that there. Sorry about that. So what do we need to add to complete the square for x squared plus 8x? Whatever 8 divided by 2 squared is equal to. I think that's 16. Add 16 on the left. I also add it on the right. And then here, for y squared minus 6y, I'm going to take the -6, divide it by 2, and square it. And that's going to be -3 squared, which is +9. I'll give you some plus signs over here. And then thirdly, 2 divided by 2 is 1, and 1 squared is still 1. So we get a 1 right there. A 1 right there. So now the whole reason we added these things on to each of these parts is so that now you can write, instead of writing x squared plus 8x plus 16, you can rewrite that as x plus 4 quantity squared. And y squared minus 6y plus 9 factors as y minus 3 times y minus 3, or y minus 3 squared. And z squared plus 2z plus 1 is z plus 1 times z plus 1, or z plus 1 squared. And it's equal to -17 plus 16 plus 9 plus 1, which I believe is 11, I think. Nope, sorry, 9. Apologies. I thought I had a 1 in my head instead of a -1. -17 plus 16 is -1. -1 plus 1 is 0, and 0 plus 9 is 9. So here, the center of this sphere is -4, comma, +3, comma, -1. And the radius is the square root of 9, which is equal to 3. Really what's going on here is we're just kind of using the distance formula to find this equation. So what we're really saying is that for this sphere that we've described, any point on the sphere, which yeah, I'll draw this down here. I'll try to draw it. I'm just gonna, well, sure. You'll maybe appreciate my drawing. Here's my sphere. I'm not trying to draw it on the coordinate axis system because I don't really need to. But I do know that my center is -4, +3, -1. And you're welcome. Any other point on this sphere has to be a distance of 3 from from the uh from the center. So like this point here, the distance between that point and that point is 3. Well, we have a distance formula, right? The distance between 2 points is the square root of the difference in the x's squared plus the difference in the y's squared plus the difference in the z's squared. This distance formula, no, it doesn't. Sorry. Right? It's true in 2 dimensions and 3 dimensions, right? You just have to add on the 3rd dimension. So for the one we were just doing here, the distance, which is 3, is equal to the square root of x minus -4 squared plus y. Bless you. I wrote -3, but I think it's supposed to be +3. It is supposed to be +3, James. Y minus +3 squared plus z minus -1 squared. And if you square both sides, you're exactly going to get back to the equation of the sphere. So just like the equation of the circle, the equation of the sphere just comes from the distance formula. But it is good to know how to find the distance between 2 points in 3 dimensions. Sure. Yeah, fine. We'll do one more thing, right? And then we'll talk about that if we have time. So last thing with a sphere here. Let's say, yeah. So we're given the following information. A diameter of a sphere has endpoints. What have I got here? Let's call the first one P, and it's 2, -1, 3, and Q is the point 4, 1, 7. Find the equation. So here's what we have. We have some sphere somewhere, and we don't know anything other than there's some diameter. So diameter, is a line a segment that goes from one end to the other and goes through the center. So that point there is 4, 1, 7. That point there is 2, -1, 3. But to write the equation, I need to know the center of the sphere and the radius of the sphere. And I would probably always recommend in a situation like this, finding the center first, because the center is just the midpoint of those 2 points. So the center is the midpoint. I'm not going to call on anyone, but raise your hand if you remember the midpoint formula. Cool. You actually know it. You just don't know you know it. Raise your hand if you know how to find the average of 2 numbers. Right. You add them together and divide by 2. That's what we're doing to find the midpoint. You're finding the average of these 2 points. You're going to say, well, the midpoint is going to equal the average of the x coordinates, 2 plus 4 divided by 2, the average of the y coordinates, -1 plus 1 divided by 2, and the average of the z coordinates, 3 plus 7 divided by 2, which in this case ends up being 6 over 2, 0 over 2, and 10 over 2. I always encourage everyone to think about the midpoint formula as just the average of your 2 points, because then it's like, oh yeah, I know what an average is. The radius now, this is why it's good to do the center first, because instead of finding the distance between your 2 endpoints and then cutting it in half, you can just find your distance from your center to either one of these endpoints, which I think is usually less work to do. So our midpoint, our center is 3, 0, 5, and then let's find the distance between 3, 0, 5 and 4, 1, 7. So this distance here, that distance is going to equal the square root of 4 minus 3 squared plus 1 minus 0 squared plus 7 minus 5 squared, which is equal to the square root of 1 plus 1 plus 4, which is the square root of 6. And that's our radius. So then we write our final equation as x minus the x coordinate squared plus y minus the y coordinate of the center squared plus z minus the z coordinate of the center squared equal to the radius squared. But really, you shouldn't leave it like that because there's a couple things that are just kind of silly. I don't need to write y minus 0. I should just write y. So this is really x minus 3 squared plus just y squared plus z minus 5 squared. And instead of writing the square root of 6 squared, let's just write that as 6. So something useful to mention here is that if you were say you were given an equation, let me just instead of just saying things, let's write things down. So we're not going to do this next problem, but I just want to point out, if I was given the equation of a sphere and I was told it was something like x squared plus 4x plus y squared plus z squared plus 8z equal to 12, I only have to complete the square for x and for z because y squared all by itself is already completed. It's really y minus 0 squared. So I'm going to show the work because I feel like I should. If I complete the squares, I said I wasn't going to do it, but now we're totally going to do it. I'm going to get x squared plus 4x plus something plus y squared plus z squared plus 8z plus something equal to 12 plus those two somethings. So here, 4 divided by 2 is 2. 2 squared is 4. Here, 8 divided by 2 is 4. 4 squared is 16. So then this becomes x plus 2 squared. This becomes, if you want, y minus 0 squared, although you do not need to write it that way. And this becomes z plus 4 squared equal to 16 plus 16 is 32. So my center is negative 2 comma 0 comma negative 4. And my radius is the square root of 32, which you could simplify as the square root of 16 times 2, which is really just 4 root 2. But the real point of that question was just to point out that if you have a variable squared and you don't have like plus something times it or minus something times it, its square is already complete and you don't have to do any work for that part of it. All right, let's end it there. Next week, we'll start talking about vectors. And not that it affects us, but just a reminder, no one has class on Tuesday. So I'll see you on Monday and I'll see you on Wednesday, but don't come to school on Tuesday because no one will be here. And apologies for not starting the video.
I also have the attendance sheet too.
Yes, you may. Yeah, it's I think right there. Yeah.
So since so are they report so we're gonna do like the first 20 minutes since